Yes, in fact, I am a nerd. It's Pi Day, everyone! As most of you know, today, March 14th, 314, is the day on which we celebrate, at least here in the United States, everybody's favorite circle constant, pi. Now, in addition to being a horror guy, some of you probably know I'm also a math guy. Yes, in fact, I am a nerd. And so I thought it would be an interesting idea to combine my interests and come up with a horror-related or spooky sort of way of empirically calculating pi. And so that's exactly what we're going to do. We're going to use a horror-themed empirical calculation to estimate the circle constant pi. But instead of using circles, we're going to use rather different items. We're going to use a small spring, a small witch's cauldron, and, of all things, a small bag of human teeth. I did tell you this was going to be a spooky, horror-themed pi estimation, did I not? And so let's get right to it. Let me start off by showing you the theory behind what we're going to do, and then we'll actually perform our measurements, and then I'll whip out my trusty calculator, and we will hopefully come up with a reasonable approximation of pi. So our calculation begins here with this equation for the period t of a spring. The period is the time it takes for a spring to oscillate when a weight is dangled from it. And notice it has pi right in there. So if we solve that equation for pi, we can get an estimation of pi in terms of the period of a spring, the spring constant k, and the mass of the object that we hang from the spring. The mass we'll be able to get just using a scale. The period we'll be able to measure with a stopwatch. We also need to calculate the spring constant k. In order to calculate the spring constant, we use this equation, which tells us that the force on the spring is equal to the spring constant times the difference in length that the force makes when it's hung from the spring. So we can solve that for k. The force becomes mass times the force of gravity, and delta L is the change in length. So what I'll do is I'll measure several masses, get the change in length on the spring, and we'll be able to take an average of those to get our spring constant k. We'll then be able to use k along with our mass and period calculations to estimate pi. So here's our little spring, and the mass that we're going to use is this small, tiny little witch's cauldron. We need to get the mass of this empty, that'll be one of our masses, and then I'll also get a couple others by putting different objects into the cauldron and determine the mass of the whole system. So first, empty, we see that comes out to be 918 grams. Let me write that down and then we'll move on. To get one other mass, let's add some little jars of coins just to see how much those do. That makes it 1,254 grams, 1.25 kilograms. To get a third measurement, I'm going to add a can of Diet Mountain Dew. That makes it 1,293 grams. And because why not, I'll add a tiny little bottle of Johnny Walker Blue Label. That makes it 1,090 grams. Those we will use to determine our spring constant. I also need to determine the final mass that we're going to use to determine the oscillation, which is the cauldron along with the little bag of human teeth that I acquired through a dental supply company because I like to collect weird things. That comes out to be 935 grams. And now we just need to determine the change in length of each of these systems. I'll do that by measuring the total length on the spring from the end of the spring to the bar from which it's hanging, and then I'll subtract the length at which there is no weight hanging from it, and that'll give us the change in length. And so for this empty one, we're at 8 1/4 inches. And by the way, I'm using inches because I'm using my trusty tape measure from my woodworking shop, and most of the plans for my woodworking are in inches. I will convert these to metric after I'm done with all of my measurements when I do my final calculations. with the teeth, we're at 8 5/16. Let's try the Johnny Walker carefully in case the whole system collapses. I don't want to lose this. It's freaking expensive. 8 7/8. And with the coins, 9 7/16. And finally with the can, 9 1/2. And now we just need to measure our oscillations. We add our teeth into the cauldron because that's the system that we're going to be using. Now, one period of oscillation is one complete fluctuation up and down as this bounces on the spring. And so all I need to do is use a stopwatch to time one period. Now, timing one period will actually be a challenge. So what I'm actually going to do is time 5 periods on the stopwatch, and then I'll divide by 5 to get the final answer. In order to be a little bit more precise, I will repeat that experiment several times, and then I'll take an average of those, and we'll use the average period for our final calculation. It's also important when you're measuring the period that you want to start it bouncing and then let it settle into a rhythm before you start your calculation or before you start timing. All right, let's get it started and see what we get. Let's get it started bouncing, wait for it to settle in for a second, and now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go, 5.05 seconds for 10 oscillations. We'll now repeat that experiment several times, and then we'll take the average of everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.77 that time. 8, 9, 10. 5.64. And I'll carry on like that until I've got enough measurements. Okay, I now have 15 measurements of the period of oscillation. I have the length measurements that I need to get my spring constant. I have the masses that I need to calculate everything. I have just one more thing that I need to do, and that's to remove the weight and get the original length of just the spring system. Once I do that, it's a little bit frigid out here in the shed, so I'm going to pack everything up and then I'll go back inside to do the final calculations. So to get that original measurement, we just take our weight off, and now this will give us the length of the spring system without any weight on it. That's 6 3/16 of an inch. I'll make a note of that and then pack everything up and head inside. When you next see me, I'll be inside where it's warmer. I'll whip out my calculator and we'll do our final calculations and see if we have successfully estimated pi using nothing but a witch's cauldron and human teeth. All right, I'm now back inside. It's cold and now dark outside, so all the better that I'm inside to do these calculations. I'm here at my blackboard so I can walk you through each step of the calculations. Don't freak out if you're not a math person. I'm going to go through this quickly and I'll explain everything I'm doing as we go. So, to begin with, as I showed you earlier, we know that the spring constant K is given by K equals mg over the change in length. And so to use this equation, we just need our changing lengths, the masses, which we measured. We also need g, which is the acceleration due to gravity. For our purposes here, we're just going to say that g is equal to 9.8 meters per second per second. That's a standard accepted value, good enough for our purposes. And it's also worth pointing out that in order to do this calculation, we need to make sure everything's in the same units. Because this is in meters per second, we're going to need our time in seconds, we're going to need our lengths in meters, and we're also going to want our masses in kilograms. So I'm converting everything into kilograms, meters, and seconds. And so, for example, the length that we measured, one of the lengths we measured was 8 1/4 inches. That comes out to 0.20955 meters. We also need to subtract from that the actual original length of the string because we want the change in length. When we do all of that, we get changing lengths of 0.05, 0.07, 0.08, 0.06, 0.05. And then for each of those, we plug each of those lengths in here with the corresponding mass in kilograms. So for example, for the empty cauldron, we'll end up with 0.922 kilograms. times 9.8 meters per second squared divided by 0.0523875 meters, and we will end up with a K value of 172.476. We'll also end up with 4 other K values because we took 5 measurements. When we average those together, we will get K is equal to 178.427. And that's the value that we're going to use in our calculation later on. Next, let's talk about our oscillations. I took 15 measurements of the oscillations to calculate the period. They were all 5 and change seconds, but each of those was 10 oscillations. So if we average all of those together, let's say we have, for instance, T1 was 5.05 seconds, T2 was 5.77 seconds, and so forth all the way through T15, which was 5.70 seconds. In order to calculate the average, we will just calculate the sum of I equals 1 to 15 of T sub I. We'll divide that by 15, and that will give us T average for the 10 oscillations. And then if we divide that by 10, because there were 10 oscillations for each, we will get our final T average value. When we do all of that, we'll end up with a final T average of 0.578733 repeating seconds as our period for one oscillation. That's the average period for one oscillation based on our measurements. And finally, we will remind ourselves of our estimation of pi, which is pi is equal to T over 2 times the square root of K over M, where K is our spring constant, M is the mass, T is our period. We have our spring constant, we have our period now, and the mass is the mass of the cauldron with teeth system that we used, and that was 0.935 kilograms. So now we have everything we need, we just need to plug it all into the calculator and see what we get. And so we will get K is 178.427, 178.4. And when we do all of that on the calculator, we will get pi is approximately equal to, there it is, pi is approximately 3.997. Obviously a little bit off from the known value of pi. Let's compute our percent error. So we will do 3.997, and we'll subtract the known value of pi, which is 3.14159. and so forth, as you can see on my shirt. Subtract that value, divide by the known value of pi, 3.14159, and multiply by 100, and we will get our error. Our error is equal to 27.24%. Okay, 27% error. Obviously not the most precise calculation of pi, but think about what we did. We measured this using teeth. I think 27% error is pretty good for a measurement of pi using human teeth as our instrument. Regardless of the error, we got the measurement that we got. We did manage to estimate pi to a reasonable precision using horror-related materials. So I'm pretty happy with this, all things considered. Perhaps next year I'll come back and do another calculation of pi with other horror-related things and see if we can do better than our 27% error. But that brings us to the end of our Pi Day celebration. Go forth, calculate pi, eat pie, enjoy horror, enjoy math, do all those wonderful things. Let me remind you, as always, please do like, subscribe, leave me a comment, all those wonderful things that help out us YouTube people. And until next time, as always, take care and stay scared.